the final talk of the conference. We have Nick Edelen. Take it away whenever you're ready, man.
Yeah, well, thanks, Jonathan and Matt, for the invitation. Right, so I want to talk about minimal surfaces. So let me go write the title down. So degeneration of 7-dimensional minimal hypersurfaces with bounded index. So, technically minimal surfaces are ancient solutions to mean curvature flow. So we're interested in minimal surfaces, and as you know, minimal surfaces are models of soap films. And okay, so I'll just write some stuff down. So we're interested in minimal hypersurfaces. So of course, minimal means stationary for area. So soap films are, well, they're probably going to be local minimum for area, but in particular, going to be stationary points. And just like the soap films they model, or in curvature flow, minimal surfaces will in general be singular. So in general, you're going to have a singular set. And for the purpose of this talk, you can think about the singular set as the set theoretic closure minus M. So for the purpose of the talk, you can think about M as just like a submanifold, and then the singular set is like the points in the closure, but not in the submanifold. And the way that you typically go about trying to understand a singular point is you look at the tangent cone. So just like in curvature flow, you take a tangent flow. So here, if you have a minimal surface and you have some singular point, you choose a sequence of radii going to 0, and you zoom in at the singular point. So you translate and dilate, and what you're going to get in the limit is some dilation invariant minimal surface called the tangent cone. And so minimal surfaces are, so singularities are modeled on cones. And so, like the natural questions in regularity theory, which a lot of people try and think about, and what I am super interested in are like, what sort of cones can you get? Like, how does the cone relate back to the minimal surface? And is this process even unique? If you take a different sequence of radii going to 0, then maybe you get a different cone. Of course, there's been several talks the past 2 weeks about this for mean curvature flow. And I'll just quickly mention, so the sort of magic quantity which makes this work is I'm sure you're familiar, is the certain monotonicity formula. So I mentioned this because we'll come back to this for a little bit. So if you look at the normalized area in a ball of radius r, then this is increasing in r, and it's constant if and only if you're a cone. So it's just like in the Huysken monotonicity, you get parabolic cones. Here you get Euclidean cones. So in general, for like a general minimal surface, these questions are very poorly understood. We know very little, almost nothing. Oh wait, there's a chat. Oh no, sorry. But thankfully, most of the minimal surfaces that you encounter in nature and probably also in math are better than just minimal. They're actually going to have some sort of stability property. Certainly if you minimize, you're going to get something which is a minimum. And even if you do some sort of min-max procedure, you'll get something which is sort of locally stable because there's only like finitely many directions which decrease area. Thankfully, we can often assume M is better than just stationary. And so let me just remind you that, so I'm sure you also know this, so minimal surface is called stable if deformations can only increase area to second order. So if I look at any sort of deformation, like is sort of identity plus t times x, and x is compactly supported vector field. And I look at the deformation of M along this vector field, and I look at its area, then the second derivative at time t equals 0 is non-negative. And this is for all, compactly supported deformations. And right, so that's stable. And it turns out, so a lot of things are stable or maybe locally stable. So locally stable is sort of the same thing, except you just require that x. So for every x, m is stable in some ball centered at x. So right at any point, there's some little ball in which you're stable. And so like any smooth minimal surface is stable, is locally stable because graphs are locally stable. So one last thing I want to mention about this is that one sort of quantification of local stability is the idea of index. So it turns out that this thing here, this second derivative is a symmetric bilinear form on the space of vector fields on your minimal surface, and so you can talk about like its eigenvalues and stuff, and the index is just the sort of the dimension of space of vector fields which decrease area to second order. So it's the number. It's sort of like the number of directions for which this second variation operator is strictly negative. And so, like if you have finite index, you're always going to be locally stable. But it actually tells you something more because it sort of gives you control on sort of like where these sort of regions of stability are located and like how big they can be. So it gives you some like quantitative control. And right, so I mentioned before, like, so these all these surfaces are very interesting because certainly, if you do a minimization procedure, you're going to get a stable surface. If you do a min-max procedure, you're going to get surfaces with bounded index. So like most of the surfaces you're going to encounter through any sort of, I don't know, like variational construction are going to like have finite index. Right, so for these kinds of surfaces, for locally stable minimal hypersurfaces, we know a lot about the regularity, and sort of the cornerstone of regularity theory for minimal surfaces is the following. So it's sort of a accumulation of many people's works. So it says that if I have if I have a hypersurface inside Rn, or maybe an ambient manifold of like a C3 metric or something, which is minimal and locally stable, and we have to assume that there are no sort of codimension 1 singular junctions. So I'll come back to that in a second. Then the singular set. The singular set is at most codimension 7. I'm sure you are familiar with this theorem. And not only is it codimension 7, it has locally finite n-7 area, and it's actually n-7 rectifiable. So it's like contained in a countable union of C1 n-7 submanifolds. So it's n-7 rectifiable. So this condition is just because, if you take like a union of half planes meeting along the edge, and that's a stable configuration, you don't usually see that when you solve minimization problems for reasons of orientability, but you could see it in a stable surface. But what this is saying is that once you rule out the sort of like junctions modeled on hyperplanes, half hyperplanes, then the singular set drops to codimension 7. And so this is true in any dimension. In dimension 7, so in the critical dimension, we actually know even more. So in this case, the singular set is discrete, and tangent cones are always unique. Tangent cones unique, and they have a smooth cross section, smooth link, and near every tangent cone, M is a C1 perturbation of its tangent cone, and M is sort of a locally C1 perturbation of its tangent cone. So this gives you like a very precise picture of the sort of fine scale behavior of any 7-dimensional locally stable minimal hypersurface. And I'll write some names down in a second. Let me just make one for Mark. So these are also sharp, and just give you some examples. So the sort of canonical examples of stable or minimizing cones are these quadratic cones. So quadratic cone is given by, so if you give me two integers p and q, then I can define the following set. X and y inside R p plus 1 cross R q plus 1. So this is a hypercone in R p plus q plus 2. And it turns out that the cones C33, C24, and C15 are all stable. And these two cones are actually area minimizing in the sense of currents. And then, in lower dimensions, of course, all the minimizing or stable cones are planes. So you can have singular sets, and usually these are the sort of canonical examples of singular sets. And actually, these are the only known stable minimal hypercones in R8. It's one of the sort of big open questions. There's been a lot of great progress on like classifying low dimensional shrinkers. It'd be really awesome if there was some progress on this problem. But who knows? So I should maybe write down some names. So these theorems are due to many people. Degeneration and Omgren and Allard sort of came up with the original sort of epsilon regularity theorems. Federer came up with sort of dimension reducing argument to relate dimension to low dimensional cones. Let's see here, who am I missing? So Jim Simons sort of classified the low dimensional cones. Leon Simon proved rectifiability. Neighbor Valtorta proved the area bound, and they gave another proof of rectifiability. And then, all right, so Neshon, Wikra, Masekera. I always think of in my head as Neshon. So Neshon and Shane Simon, basically, so all the stuff before that was like morally for minimizers, and then these two last results sort of extended it to stable guys. So that's okay. So that's like a little bit of history. That's the kind of state of the art for a regularity theory for stable minimal hypersurfaces. Are there any questions?
Yeah. So can I ask, so for n equals 7, if you want to bound the number of singular points, is this a simple argument, or do you need this whole neighbor-Valtorta machinery?
Well, so the neighbor-Valtorta argument boils down to a very simple argument. It's like a one-page argument. Oh. You just like there's a short contradiction argument which says that like if your density drop is small than the singular in a ball, then any singular points have to be very close to the origin, and then you can just sort of use the summability, the monotonicity of density to say there's only like finitely many scales where the density drop is big, and then that tells you that gives you an a priori bound in the number of singular points.
Oh, amazing.
Right. So that actually maybe sort of segues into what we're interested in this talk, because so they proved an a priori bound in the number of singular points, and so what we're interested in this talk is not just like a fixed minimal surface, but like moduli spaces of minimal surfaces. So like moduli spaces of 7-dimensional minimal hypersurfaces. And in particular, what this sort of boils down to is understanding the sort of uniformity of these estimates, or rather these estimates. So these estimates tell you, like, if I have a fixed minimal surface, there's, around a singular point, there's some scale at which, you have control. In fact, at any point, there's some scale. But if you want to look at sort of families of minimal surfaces, you have to have control of like the size of that scale at which you have good control. And in particular, what I want to know is sort of like, so neighbor-Valtorta's estimate tells you you can only have like a controlled number of singular points along a sequence. But what I want to know is that can you also have controlled geometry or topology along a sequence? Like, could you have, like, if you had a, so I'll actually write down a question. So the question which I'm really interested in is the following. So suppose I have a sequence of stable minimal hypersurfaces inside, the unit ball is symmetric, and they all have optimal singular set. And let's suppose they converge to some cone. So convergence is like varifolds or measures, or basically whatever you want, Hausdorff distance with some other metric. And let's say, of course, the metrics have to converge as well. So I have a sequence of minimal surfaces converging to a cone, not necessarily a blow-up sequence, just like some random sequence. And then what I want to know is what can you say about the MI in maybe a slightly smaller ball? So in particular, could you have like a sequence of surfaces with like worse and worse topology collapsing into a singular point of some cone? So for non-stable surfaces, you can definitely do this. Like if you take like the blowdown Shirk surface, you'll converge to like a pair of planes, have like worse and worse topology. But here we only have isolated singular points, or okay, in dimension 7. So like, could you have like a sequence of like more and more handles collapsing into an isolated singular point or something? And the reason why this is interesting is because if you want to answer global questions about moduli spaces, like the number of diffeomorphism types, this is exactly the question you're going to confront. Like what happens in these sort of weak limits. So let me give you sort of a very important example, which is probably also familiar to many people. So if you take the Simons cone in R8, so it's a minimizing cone. So all my cones just are X's. So it turns out it was proven first by DeGiorgi, Biombieri, DeGiorgi, and Gusti first for the Simons cone, and then for any minimizing cone by Hart-Simon, that you can foliate the complement of the Simons cone by a family of smooth area minimizing hypersurfaces. So it looks sort of like this. And they're asymptotic to the cone at infinity. So even for minimizing surfaces, if you start scaling down these leaves, in fact, all these leaves are just scales of each other. So if you scale on these leaves, then you're going to converge to the cone, but there's going to be the sort of regular and singular structures change in the limit. So all the MIs are smooth, but the limit, the singularity appears out of nowhere. But at scale 1, they look closer and closer to the cone. And so this is not, something funny is going on. Like you can't, like these MIs could have like a genuinely different structure than the original or than the cone they converge to. Even in the nicest case of like minimizers. So let me also mention, so this example was kind of, was hugely elaborated on recently. So I'll write this down. So this was done by Biombieri, DeGiorgi, and Gusti, and also Hart-Simon for any minimizing hypercone. And then Leon Simon just recently has this amazing result. It's like incredible, where he showed that you can have a sequence. So not a sequence. Well, you could have a sequence. So he showed the existence of an 8-dimensional stable minimal hypersurface inside R9 with some smooth metric, and you can get the 8-dimensional. You can get the surface to look as close as you want in like the varifold sense to the cone cross R. And you can get the ambient metric to look as close as you want to Euclidean metric, but you can prescribe the singular set to be any pre-assigned closed subset you want. So the singular set is always closed. And so what Leon showed is that if you take Simon's cone across R, then sort of what you can do is, you pre-assign let's see. So you pick your favorite closed subset of R, and then you build a surface which looks like sort of the slices at K, look like the cone, but then as you move away from your prescribed singular set, you sort of lift off into the foliation. So as you move along this axis, you sort of lift off into the foliation away from K, and then you pull down to the cone at K. And so you build something which looks very close to cone cross R with arbitrary singular set. In particular, this tells you, for the purposes of what I'm talking about, this tells you that there's like no hope of answering your question in higher dimensions when n is at least 8 for smooth metrics. I mean, Leon, I think the sort of natural follow-up question is whether you can do this in an analytic metric, and I think the consensus is that maybe you can't, but we don't know. Right, yeah. So if you take, you take the sequence, you can you can get your minimal surface to look closer and closer to the cone cross R, but you have zero control over the singular set, so you have like no idea what's going on. And then, so to contrast this, I want to point out in lower dimensions, this question is basically entirely answered. So in dimensions where you don't have any singular set, so when n is at most 6, then if you're stable, then the only cone you can get is a plane with multiplicity. And in this case, the results of Shane-Simon and Neshon tell you that the MIs are smooth graphs over C. So this is if the MI are stable. So we understand entirely what happens in low dimensions. And even if the MI aren't stable, but they have bounded index, so if instead the index is uniformly bounded, then there's been several works recently considering this. It turns out the MI, they're not going to be graphs because there could be like at most I points of index concentration where your convergence fails to be smooth, but it turns out that the MIs still have control geometry and topology. You can sort of control what's happening at those points of index concentration. So the MI have controlled geometry and topology. And so this was first proven by Otis and Dan and Davi, Kedivar, Maximo, and then Rito Luzzano and Ben Sharp gave a different proof with some other sort of quantitative estimates. And again, the point of doing this, like this isn't just some sort of academic, well, I guess everything we do is an academic exercise, but this isn't just like even more academic because, the point is that this gives you global information about these surfaces. So using this sort of degeneration result, they were able to show that in low dimensions, there's only finitely many diffeomorphism classes, diffeotypes of minimal surfaces inside a fixed closed Riemannian manifold whose area is bounded and whose index is bounded. So if you, in low dimensions, if you're in a closed manifold and you restrict hypersurfaces, with controlled area and index, then there's only finitely many diffeomorphism types. And this is essentially a direct consequence of their degeneration theorem. And so, what I'm interested in this talk is this critical dimension. So it turns out in dimension 7, you start to see singular points, but it's still not in this sort of like wild west of the higher dimensional case. Like there's still enough control where you can actually say something. So that's my theorem. So that's where I'm headed. Maybe I should make one more. Maybe I'll make one more comment before I state my theorem. So I apologize. So sort of it's one more example in some sense. So in general, if you're trying to sort of study these degeneration results, so let's go back to this question. You have a sequence of minimal surfaces limiting to the cone inside the ball. And And so in particular, on like a bigger and bigger annuli, you look very close to the cone. And so what you could imagine doing, like a very natural thing to do, is to pick a good sequence of radii and blow up at that sequence of radii. And in the limit, you would get an entire minimal surface in R8, which is asymptotic to the cone. So for example, like, you might get like a leaf of the Hart-Simon foliation or something. And in general, you sort of expect a sort of dictionary between sort of stable minimal hypersurfaces in Rn+1, which are asymptotic to C, and the sort of local pictures of the MI converging to C. So, you'd expect that if you can like classify, stable minimal surfaces asymptotic to the cone, you should be able to say something about how surfaces can degenerate to that cone, in a ball. Of course, there's even making this sort of dictionary work is like fairly technical, but in some special cases there, this is done. So there are 3 cases I wanted to mention in particular, special cases. So of course, if C is a multiplicity 1 plane, so the famous Allen theorem tells you if you converge to multiplicity 1 plane, then you're regular. A sort of one way you could think about this is that like if you have a minimal surface which is asymptotic to a multiplicity 1 plane, then it has to be a rotation or translation of a plane. So you like entirely, all the sort of like models. Another example, which might not be quite as well known. So if you take a union of 3 half hyperplanes in any dimension or codimension, then it turns out that there's a good sort of answer to this question. So Leon Simon proved that if you have a minimal surface that's sufficiently close to one of these cones, then you're a C1 alpha perturbation of this cone. And sort of another way of thinking about it is like, if you have a minimal surface which is asymptotic to the y, then it has to be a rotation or translation of the y. And the last example I wanted to mention is that if your cone is a minimizing quadratic cone, then Luke and I proved a year or 2 ago that if you have a sequence, if your MIs are sufficiently close to minimizing quadratic cone, then you have to be a C1 alpha perturbation of either the cone or the leaf. And this is kind of reflected in the fact that so Simon Solomon, like 20 years ago, proved that the only minimal surfaces asymptotic to a minimizing quadratic cone are either the cone itself or the leaves of the foliation. So of course I should say multiplicity 1. So I'll say the theorem. It's a little bit of writing, but I think it's kind of cool. The corollary will be shorter. So the theorem is the following. Suppose I have a sequence of minimal surfaces inside a sequence of balls with some metrics. So minimal, uniformly bounded index, and optimal singular set, so no codimension 1 junctions. And let's suppose that the MIs converge to some cone possibly with multiplicity, as varifolds or measures. And of course, we have to assume the metrics converge. So let's say you converge the Euclidean metric in C3. Okay, so the conclusion is that you can pass to a subsequence so that, so I'll say this, but probably won't be able to elaborate. So the MI, so if you pass to subsequence, then you admit what I call a cone decomposition, which is sort of a version of the bubble decomposition for harmonic maps. But okay, more concretely, what you can say is that there's some radius, and you can find bi-Lipschitz maps from the ball of that radius to itself, which parameterize the ith minimal surface by the first minimal surface, and that take the singular set to the singular set. And and away from the singular set, C2 diffeomorphism. and they all have uniformly Lipschitz bounds. So what this is telling you is that you can only sort of collapse into a singular point with controlled geometry topology. So we don't have any like classification of 7-dimensional stable minimal hypercones, and we certainly don't have any classification of the surfaces asymptotic to those guys, possibly with multiplicity. So I can't give you like a precise picture of like what these look like because we don't even know what the models should look like. But I can tell you that there's some sort of finiteness theorem that you have to have sort of like finite topology and geometry collapsing to the singular point. And there's like some sort of quantitative control as well, which I don't know, I thought was cool, but it's maybe not super useful at the moment. So then, okay, so the main corollary is that if you consider the space of minimal 7-dimensional hypersurfaces inside a closed 8 manifold, with bounded index and area, why did I do that? So and of course, as usual, we want optimal singular set. Then this space, so any one of these minimal surfaces satisfying these properties fits into finitely-many diffeomorphism classes. Diffeo classes. And M bar into finitely-many bi-Lipschitz equivalence classes. So remember, M, for all intents and purposes, M is just like a submanifold, like a smooth submanifold. And so I claim that if it's 7-dimensional, you might have a singular set, but if you have a priori index and area bounds, then the submanifold itself fits into one of finitely-many diffeomorphism classes, and if you extend it, to its closure to include the singular points, then that fits into one of finitely-many bi-Lipschitz equivalence classes. Right. So that's the theorem and the corollary. So yeah, it's kind of like a smooth version of like Naber-Valtorta. So Naber-Valtorta control the number of singular points. So this controls the sort of like diffeomorphism types and in some sense the geometry.
Nick, can I ask you a question? If you have two cones, if you have like let's say I have something multiplicity 1 limiting to a cone with multiplicity 2, or a piece where it looks like that, is your model like separated and it maps them to one point? Is it like an immersion type picture, or are you like I don't know if that question is.
Well, there's no immersion, so everything's embedded away from the singular points. But so if your cone had multiplicity 2 and you blew up, then yeah, you would have like a stable, well, let's say index is 0. So and then you'd have like a stable minimal hypersurface asymptotic to the cone with multiplicity 2. And so like that's even, we have no idea. Like, so in principle, maybe you could have something where like you have these like two sheets and then they come together, maybe they're joined, or maybe you have like two leaves of the foliation which are joined by like catenoids, or they're joined by some singular point.
That costs you an index by the one-ended theorem, right?
Yeah, you're right. Yeah, so if you're stable, that probably can't happen.
But you could have an index. You could have an index 1 picture like that. Right?
You're right. So yeah, if you're stable, then you wouldn't be asymptotic to the cone with multiplicity.
What I'm just asking about is the statement of your theorem says you have your MIs, and then what can you can map them to something.
After you pass through subsequence, all the MIs are diffeomorphic to each other, or bi-Lipschitz to each other.
Oh, okay. And those are not maps defined on the ambient manifold, just on the submanifold.
No, they're defined on the ambient. They're defined on the ball, on the ambient ball. So this is why you only get Lipschitz bounds as opposed to bi-Lipschitz bounds, because you pass to subsequence and then they map the first guy to the ith guy. So the image in your head should be like, this is your first guy, and then the ith guy gets more and more collapsed to the cone. The Lipschitz bound of the inverse is going to blow up.
I see.
And likewise, maybe if you have multiplicity, then you could have sheets coming together more and more. And so like for any particular I, they're going to be bi-Lipschitz maps, but you're only going to have uniform Lipschitz bounds because the sheets collapse more and more together. And in the limit, you're going to get something which is only Lipschitz, not bi-Lipschitz.
All right, cool. All right, thanks.
So this tells you only have like finitely many diffeomorphism classes. But if you expanded yourself from finitely many to countably, then you would get uniform. You could get uniform bi-Lipschitz bounds. I can tell you a little bit about how the proof works. So there's basically two key ideas which are very much indebted to the Blowup-Simon inequality. So the key idea / observation 1. So I call this really an observation because it's not even my observation. What this says is that if you look at the set of densities of cones, so you look at basically like the area of the length in the set of 7-dimensional cones in R8, which are smooth and stable, then this is a discrete set. So this is I don't really want to go into the proof, but it's like if you're familiar with like Blowup-Simon inequality, then it's a direct consequence. Oops. Blowup-Simon inequality plus the sort of standard regularity and compactness theorems for stable minimal hypersurfaces. Right, because Blowup-Simon tells you that like if you have an analytic function, then the difference of a function, the difference of function values is bounded by the gradient. So if the gradient vanishes, then they have the same value. And so what this tells you is that we can, or what the idea is that you could induct on the density of the cone. So loosely speaking, you have your fixed cone, and you have your MI, which are getting closer and closer to the cone. And so what you'd like to do is some sort of blow-up argument, which I suggested earlier. So on bigger and bigger annuli, so like MI in the annulus from 1 to RI looks very close to the cone. And then if you are very clever with your choice of radius, and you have to sort of translate things a little bit around as well. So, but let's ignore that for the moment. So if you rescale, then you get some minimal surface inside R8. And we'd like to say, so there's sort of an asterisk at this point, but you can show that this limit is asymptotic to the cone. So I'm basically just going to draw the same picture again. So you got your M, you got your C, and you got your M prime, which is asymptotic to the cone, and you have ball of radius 1. Outside the ball of radius 1, the M prime is going to be smooth because you converge smoothly, in these annuli to the cone, and so any sort of weird singular behavior or any sort of pathological topology has to happen inside these small balls. And so any sort of weird pathology, any weird topology or geometry in the limit is going to, appear inside this ball here. And so if your M prime is totally smooth, then you win. You basically get a contradiction because on the one hand, in these annuli, you're all diffeomorphic to the cone. But on the other hand, inside these small balls, you converge smoothly to the rescaled M prime, and so you're all diffeomorphic. And so, passing to subsequences. And so far out in the sequence, all the MIs are going to be diffeomorphic. And so if your limit is smooth, then you're good. But then, okay, so in general, these minimal surfaces might have singular points, but so let's say there's a singular point. But it turns out, so on the one hand, the density of M prime at infinity is the same as the density of the cone. But on the other hand, if you choose your radii in a very clever way, you can ensure that the MI primes are not cones. So there has to be a definite density drop from infinity to scale 1. And so that tells you that if you had a singular point of your limit, so let's call it x, then the density has to be strictly smaller the density of the cone. And so, and since they're discretized, that means it's like at the next energy lower. And so then you could do another blowup argument. You could sort of repeat the whole blowup argument inside a small ball centered around this singularity and prove that like all the MIs are like bi-Lipschitz or something inside that small ball. And so, so by carefully choosing your sort of blowup radius, you can blow up in such a way that any singular points are going to have strictly less density, and then you can blow up again and blow up again, and every time you sort of recurse, you're going to drop a density level until you get down to density 1, and the only density 1 cone is a multiplicity 1 plane. It's not like a very profound idea, but it's cute. So that's kind of like the basic idea of the proof, modulo various technical details. There's one very important technical detail which I want to mention, which is the second key idea, which is actually a huge issue for a little while. I was like not sure how to deal with this. So it turns out that when you one of the things I swept under the rug when I explained this sort of blow-up idea is that you only have convergence smoothly on compact sets. And so you can only pass information between finitely many scales. So like maybe scale Ri and scale 10 Ri or something. And in particular, the blow-up argument itself cannot pass information between scale Ri and scale 1. And so, so it turns out this blow-up argument doesn't tell you that this whole annulus is a nice graph over the cone. What it tells you is that at every radius between 1 and Ri, there is some cone which might be a rotation of your cone, so that you're sort of nearby that radius, you're a graph over that other cone. So in other words, like the cones could sort of rotate very slowly as the radius changes. And so actually what you get for all radii between Ri and 1, that the Mi inside, let's say the ball of radius R minus ball of radius R8 is a graph over CR, and CR is some cone which, whose link is diffeomorphic to C and has the same density, but might not be C itself. So it could be a rotation, or it could be some, maybe like pathological, some other cone. We don't know, we don't have a classification of these cones, so it could be something very weird. And so the picture is like, you could very slowly spiral like this or something. Or another way to think about it. So maybe like if you fix a cone, then you could and you fix element of the Lie algebra, then you could rotate very slowly. So like log, it's a very small number times log R. You rotate this guy. So you could get a minimal surface whose slice in the sphere of radius R is like a very slowly rotated version of your cone. And so the reason why this is bad, so if your cone was only rotating, this actually wouldn't be a problem, because you could arrange, or the reason why this is bad in any sense is because, in this annulus, of course, whether or not you rotate, you're still diffeomorphic to, the link across an interval. But the issue is how you glue in this annular region to the other regions. So the issue is how you glue this piece into this piece and the piece out here. And so in some sense, your gluing map is the map which takes the link at this scale to the link at this scale. And if your cones are really purely rotating, then you can sort of arrange this map to be a small perturbation of rotation, and there's not really any problem. But the issue is they could be other things besides rotations. Like we don't know. So this, if your cone is not integrable through rotations, there could be like a family of cones which deforms the link, but whose densities are all the same. And like the worst thing you could imagine, so say like for simplicity, you're just in like, you're in R4, and say you have a 3-dimensional cone whose link is like a genus 2 surface. And if you had a family of cones such that the link sort of fixed the top handle but rotated the bottom handle, then that family of cones would be really bad, because if you rotate it lots and lots as the scale goes down, then the sort of gluing maps are not going to be isotopic. You know, you have like, so every time you rotate by 180 degrees, you'll get a new isotopic class of gluing map. And so if you can't, so this blowup argument by itself cannot control the diffeomorphism types, because you could have these sort of pathological family of cones, which completely destroys any control you have over gluing between the outer and the inner radius. So it turns out what you can do is you can prove that actually a posteriori, after you sort of do this blowup argument, you can show that you don't actually rotate. So you can prove an estimate which morally says that small density drop implies you stay graphical.
Nick,
Yeah,
is this an application of Voyasevich?
exactly. Yeah. So so this is maybe I'll state the theorem and then I'll sort of talk about it for just like 1 or 2 minutes and then I'll shut up. So the key theorem. I'll put Leon. So the genius here is really Leon, and like all I did is sort of realize, oh, you know, you could slightly modify what he did to do what I need to do. And I'm sure if he wanted to do it, he could, but for some reason he wasn't interested in this. So so it's sort of really Leon's theorem. But so the theorem is like, if you have a smooth minimal cone, so of course smooth by meaning smooth cross section, you know, let's say you pick an epsilon bigger than 0, then all right, so then there exists delta, so that if you know, you have a minimal surface inside the ball, and let's say, you know, the metric's close to Euclidean in C3, and okay, and I want to assume that the density at scale 1 is very close to the density of the cone, and the density at scale rho over 2 is very close to the density of the cone, and at scale 1 we're a nice graph. Over the cone with like small norm. So the picture is like you have this cone, and then sort of at this scale you're a nice graph, but then you have small density drop from scale 1 to scale rho over 2. And the conclusion is that you can push the graphicality all the way down to scale rho. So m inside the ball of radius 1 minus the ball of radius rho is graphical with, like, you know, the usual estimates. Okay, so without this minus delta, this is basically exactly what Leon Simon proved in his asymptotics paper, because he was interested in unique tangent cones, and there the density is always at least the density of the cone. But that's not enough for these transition regions, because for these sort of, when you do a blowup argument, all you know is the density is close to the cone, but it could be above or below. And so so what I did is I sort of realized that if you allow the density to be close to the cone without any sort of sign restriction, then you can't prove decay, but you can still prove smallness. And that's enough to show that so it's an a priori estimate, but it's enough to show that graphicality sort of propagates as long as the density drop is small, or the density is close to the cone. And yeah, so here you use Lipschitz, you know, it's the standard sort of 3 annulus type lemma. So I meant to mention this, but one, just sort of like a, well, you know, to try and like pretend like I'm fitting in with the mean curvature people. So these arguments would apply verbatim to like harmonic maps or energy minimizing maps. And so it's conceivable that like anytime you have a sort of variation problem at the critical dimension where you start to have isolated singularities, then you could do something like this. So maybe in some suitable class of shrinkers or translators, you could apply this argument.
So maybe to connect with the open problem session. So you mentioned this example of Leon Simon, where he has this prescribed singular set, any closed subset essentially. Is there any hope to do a parabolic version of that example?
Yeah, that would be super cool. I mean, so it seems like So the thing that kind of makes it work is this picture here, is that you have, for the Simon's cone, which is singular, you have an entire minimal surface asymptotic to the cone, which is smooth, and it sort of fits into this family. And because like essentially what you do, you use this as your model, and so like you can sort of push into the foliation to make the singular set disappear and then shrink back to the cone. So yeah, if you have some sort of singularity model with this property, then it seems like you could potentially do something similar, maybe in parabolic setting. I mean, maybe you could even do it with the Simon's cone, do something along the time axis or something. Yeah, it'd be super cool.
Since you mentioned it, I don't know if it's a reasonable question, but we also had this question in the open problem sessions about flows with finitely many spherical singularities. And so just because you mentioned the sort of isolated singularity situation, I mean, is there a statement if you restrict to that class of flows, or if you could prove that conjecture?
So you restrict to the class of flows whose only singular points are modeled on Schrödinger's spheres? And
yeah, so I think maybe some class of flows with only.
Yeah, the question is like examples have finitely many neck pinches, right? So the question is, can you have countably many neck pinches or not?
I'm not sure. I mean, like, I don't know. Off the top of my head, I don't know. First thing I would try is like some sort of like density argument, like in Naber-Valtorta, like where, like more like the bad picture eats up density, So if you have singular points that are too far away from the origin, or maybe they're too elaborate, then you like eat up a certain amount of density drop. And then the fact that your density is monotone and finite tells you with like finitely many sort of bad pictures.
We should thank Nick again, but I also wanted to just thank all of our speakers for the conference, especially our two chairs, so Bill and Natasha.